The directional derivative of a vector. Let's begin by looking at the directional derivative of a Cartesian vector to see why we might be interested in looking at all this. The directional derivative shows up in a couple of vector calculus identities. Here are the two identities. Gradient of a dot product, curl of a cross product. And you see right here and here and here and here. Look, u dot del is an operator. It's interpreted as the directional derivative operator acting on a vector. And you here and here and here and here. And this is what that vector dot del operator looks like in Cartesian coordinates. Partial derivatives, u, v, w in front of the partial derivatives. And it is said that the operator is applied to each component of the vector field. Here I've called it F. And this is what it would then look like. V dot del on the first component, V dot del on the second, V dot del on the third. If you look at the result, you realize this could be written as a matrix. It's the Jacobian matrix times the vector UVW. But it turns out that the application of this operator to each component is actually an effect, because if you take this operator and act on this vector, where I, j, and k are unit basis vectors in Cartesian coordinates, what you get is the operator acting on F. It really is F times I, but I is constant, so it acts only on F. And here it acts only on G, and here it acts only on H, and hence this statement, apply the operator to each of the components. Here's another place where I've found the directional derivative showing up. It's in defining the shape operator for a surface when you're trying to talk about curvature on a surface. So this is the shape operator. It is a mapping from a vector in the tangent plane, that's what V is, to the negative of the directional derivative in the direction of that tangent vector of the surface normal, unit surface normal. And when you go to look to see what they mean by this derivative, you'll see things like this. It's the derivative of each component along the curve in the surface that has V as its tangent vector, and the derivative is taken of the component, and notice that the basis vector, the Cartesian basis vector, is sitting outside that derivative. Can we realize this in Maple? Well, let's do it with Maple commands. So here are some Maple commands to set things in motion, work in the vector calculus package, some typesetting things to make the notation a little bit cleaner. F is a free vector, components F, G, H. G is the vector field version of that vector. V, direction vector, it's a free vector. W is the vector field version of that direction. Here we imitate the notion of placing the del operator on each component of F and dotting that with the vector V. So map del onto F, and then map the dot product using V. The result looks correct, but it's a free vector. If you do it with the directional diff command, this is a vector field. This is just a free vector, but you get a vector field that looks correct. You can even write w.del and apply that to G. Now here you have a vector field, and this is a vector field. It comes out looking correct, and it's a vector field. What about doing this from first principles, using the idea that is used in multivariate calculus to get the directional derivative of a scalar? The way that's done for a scalar is you evaluate the scalar function along a line, right? A plus tu, b plus tv, c plus cw. That's a line. You take the derivative, evaluate at t equals 0, so you're sitting here at abc. Really, you take a limit, but here for smooth functions, you just set t equal to 0. And the result is, and you can see here, derivative, UVW. It's really gradient dot direction vector. Now, can we do that in the vector case? So we need a curve in R is XYZ, P is a point, ABC, TV, that's, V is the direction vector. And we end up with this set of equations, because we use the equate here, x equals y equals z equals, so we can make a substitution. All right, so we evaluate the vector f using these equations, and so we get the three components FGH with arguments along this line. Then differentiate that with respect to t, set t equal to 0, and you look and you say, okay, these are derivatives. It looks kind of messy. You have ABC, but ABC that's really XYZ. That's what I do over here. I replace ABC with XYZ. And here I've switched from this denotation to partial derivative notation, which is, to me, is easier to read. And once the arguments become ABC, then Maple says, oh, you told me to write those derivatives as subscripts with the typesetting command earlier on. And so you see we have gotten what we're supposed to get, apply the gradient to each component and dot that with the direction vector. So the real issue here is, how does this stuff translate over to non-Cartesian coordinates? I picked polar coordinates. We begin by looking at polar coordinates in the scalar case. And there I even begin with an example. So some initializations. I have taken a Cartesian function, x squared y cubed, a point, a direction, and a line in Cartesian coordinates. The function g is evaluated along the line. Take the derivative, set s equal to 0. This is the directional derivative in Cartesian coordinates. And let's use directional diff on that same problem, and we get the same answer. So I'm setting up a test case here, making sure that I can get back to this if I work in polar coordinates. So how can we describe that line in polar coordinates? Well, here it is in Cartesian coordinates, x and y. Radius, sum of the squares of the components, square root. And the arctangent gives you the angle. So RT gives you the polar coordinate description of that line. And this is a graph of these two components. There's where you start, and it is a straight line. So we can apply first principles now. G evaluated at x, which is r cos t, y, which is r sine t. Take the derivative with respect to s at s equals 0, and we get the right number. So by first principles, we can work in polar coordinates, at least in the scalar case. How about getting the directional derivative in polar coordinates of a scalar is something like gradient dot direction vector? Let's see if we can do that. So gradient applied to G evaluated in polar coordinates, right? X equals R cos theta, Y equals R sine theta. And you got to tell Maple that the gradient is taken in polar coordinates. And then evaluate that gradient. And you need to use the eval VF command because you're getting from the gradient a vector field, and you got to evaluate using this eval VF command. You evaluate at this point, but the point has to be given as a vector, and the radius here is root 13, right? 2 squared is 4, 3 squared is 9, so root 13, arctan 3/2. So that's the vector in polar coordinates. This is the gradient in polar coordinates. This is the r basis vector. This is the theta basis vector. Okay? Now you need the vector in polar coordinates. So you got to make it a vector field. Vector, you tell Maple, hey, this is in polar coordinates, and then evaluate that because there's a theta that'll be floating around at arctan 3, 2. You get this vector in polar coordinates, and you take the dot product, and you get what we have up here. You get the right value. So all of these ways of getting the directional derivative of the scalar in polar coordinates helps us understand what we have to do when we want to do this for a vector. So far we've done an example. How about in the general case? I call this the symbolic case. Polar coordinate equivalent of the Cartesian vector uv. So let's work in the student vector calculus package, some notational stuff. First thing that you try, map to basis this vector uv. It's a free vector uv. And it's in yellow because it's a caution. It comes back with this strange representation. Think about this carefully. What you see is Maple interpreted this free vector as a point, and this is Maple's in the student vector calculus package. It's the representation of a point translated to polar coordinates. You have to have the direction as a vector field in order to get the appropriate change to a vector in polar coordinates. See the bars over the E here. That tells you that these are the moving basis vectors in polar coordinates. And if you did this by hand, you would discover that I and J can be represented in terms of the basis vectors ER and E theta. And this is what will happen to the components. So this is the way you have to get the equivalent of your direction vector in polar coordinates. Okay, using this same approach from first principles, we define R and the angle. I use T for that. This is the R, this is the angle, and I'll base it at the point whose coordinates are XY for generality. Okay, so let's evaluate F at R and theta. Take the derivative with respect to S, set S equal to 0, and X is really R cos, and Y is really R sine. And we simplify, you want R to be positive, and put the angle between minus pi over 2 and pi over 2 so that the arctan will simplify back to T, at least in that range. This is the component of the direction vector. This is a derivative. This is the component of the direction vector. This is the derivative. Can we clean that up any? Well, if we convert this to derivative notation and get rid of this D notation, then this typesetting up here will write the partial derivative as a subscript, which I find much easier to read. So this is the partial with respect to r, this is the partial with respect to theta. I'd like to break this up because this r will cancel here, but not here. And so I use the collect command, and you split this plus this. Can we get the directional derivative as gradient dot direction? Well, gradient in polar coordinates dot the direction in polar coordinates does give you the same thing we got from first principles. Finally, does Maple's directional diff command work in polar coordinates? Well, let's take a look. Here's the directional diff command applied to f of r and theta in polar coordinates. This is the direction vector. Notice just write down the two components, u and v. But when you tell it polar coordinates, it applies. And we do some simplifying. R greater than 0, take care of the theta so that the arctan comes back as t. Denotation for derivatives. We never told the command that u and v formed a unit vector. So let's make this 1 by brute force. Just set it equal to 1. And by converting to diff notation, Maple drops the denotation, it puts the partial derivative symbol, but because of the typesetting, it becomes a subscript, so FR, FT, and you want to split this because this R will cancel with that R, so we use a collect command, and this expression and this expression are the same, so we got it from first principles, we got it as grad f.w, and we got it from directional diff command. For a scalar, we can work in polar coordinates. With that background, now we want to think about, can we do any of this stuff in the vector case in polar coordinates? Well, now for the vector case. Let's do an example. Directional derivative in Cartesian coordinates, for this example, convert it to polar coordinates. So, preliminaries, student vector calculus package, a vector field in Cartesian coordinates, x squared, y cubed, x cubed minus y squared, and a direction. And for the direction, you can take a rooted vector, so that includes the base point 3, 4. This is a convenient base point because the radius for this point is 5. Components uv. Let's try directional diff. In Cartesian coordinates, this ought to work. So vector, direction, get this value. Now, let's take this vector over to polar coordinates. Map to basis. That's the change of coordinate command for vector. And you change into polar coordinates. There'll be a t around, so the t is arctan 4/3. This is what results. So for this example, Cartesian over to polar, do the directional derivative in Cartesian coordinates, bring it to polar coordinates. If we work directly in polar coordinates, this is the target we should get. Now let's try using Maple's directional diff command in polar coordinates. So let's take the vector field F, this Cartesian vector field F, over to polar coordinates. Well, you see an r5th. Well, you would expect that. You're going to get an r squared here and an r cubed here, and you get an r5th. Now, here, from the x squared, you're going to get a cosine squared. But why do I have a cosine cubed? Well, when you change coordinates and you change the basis vectors, you pick up sines and cosines, and you pick up a cosine in this term, and you pick up a sine over here. So this is a vector field that you're going to differentiate. now brought over to polar coordinates. Now you want to take the direction vector over to polar coordinates. So because v is defined as a rooted vector, you can bring it over to polar coordinates. Take the directional diff, apply the directional diff to the vector g in this direction w, reminding Mabel that it's to work in polar coordinates. There'll be a t floating around, and the t is arctan 4/3. Lo and behold, the result is the same thing as we got when we worked in first Cartesian coordinates and brought that over to polar coordinates. So the directional diff command will work on a vector in polar coordinate. Can we get the same result working from first principles? Now to do that, we need a representation of the line along which we're going to work. So here's R and the angle. Let's take the components of the vector field G and make functions out of each component so it's easier to make substitutions. So this is the first component in polar coordinates, second component polar coordinates. And so we need a representation of the vector in polar coordinates. So here is f evaluated at r and theta. But you have a e sub r, you have the r basis vector. It's a function of t. I just use this representation so that when I take derivatives, I can see what happens to this vector, plus the other component, g, with the other basis vector, which is also a function of t. And they're they have to be evaluated along that line. So we take the derivative, set as equal to 0, and we have this stuff. And what do we see here? We have derivative of the basis vector. Derivative of the basis vector. And here's the basis vector, and here's the basis vector. So what do we do there? Okay, so the derivative of the basis vector evaluated at this arctangent, I just want to call it by a simple name. But if you look at the derivative of the basis vector ER, which is cosine sine, you get minus sine cosine, which is the basis vector in the t direction. And you take the derivative of the basis in the theta direction, it's the negative of ER. So just literal replacements for those derivatives. There's the ET, there's the ER, but this ER is still evaluated at this arctangent. So again, just brute force replacement. If you got the arctangent 4/3 in there, just put ER. If you have ET evaluated at the arctangent, just put the letter ET. Now it's a little bit smaller, easier to read. And let's collect with respect to the basis vectors. And we have this component with respect to ER and this component with respect to E theta. And if we write it as a column vector, this is the first component, this is the second component. It is exactly what we got up here. So you can do this working from first principles. It does work, and it gives you the right answer. Well, this is an example. Can we do these calculations for the general case? So I call that the symbolic case. Okay, now we'll take a little bit closer look. What is basis vector ER, cos theta, sine theta? Basis vector ET, unit vectors, minus sine, cosine. When you take derivatives of these basis vectors, the derivative of ER with respect to R is going to be 0 because there's no R there. If you take the t derivative of this vector, you will get minus sine cosine So that's ET. There is no R in ET, so the R derivative is 0. And the T derivative, this becomes minus cos. This becomes minus sine. You take the minus sign out, and you're looking at ER, so minus ER. Now, the operator ought to be the gradient operator with basis vectors. Will that work? ER partial R plus ET partial T over R, because if you remember what the gradient looks like in polar coordinates, using unit basis vectors, you get this factor, the scale factor 1 over R shows up. Now we need a direction vector. Well, the direction vector in polar coordinates is AER plus BE theta. Now, suppose we want to apply this operator formed by vector and derivative. What will it look like? Well, dot product, so ER dot ER will survive, and ET dot ET it will survive because they're unit vectors, and ER dot ET or vice versa, they're orthogonal vectors, they won't survive. So what's going to show up? A partial with respect to R, B partial with respect to theta over R. So is that the equivalent operator for what we saw in the Cartesian case? Let's try that. Operator acting on a polar vector, F ER plus G E theta. Well, you're going to get 4 terms. Partial with respect to R on each of these 2 terms, and partial with respect to T here on these 2 terms. Okay, so A partial R on this product, A partial R on this product, B over R partial theta on this product, B partial theta over R on this product. And now you have to differentiate these products correctly. This product, differentiated with respect to R, is just df/dr, because the derivative of ER with respect to R is 0. There's no R in that basis vector. Now you look at this term, differentiating with respect to R on ET. Well, again, there is no R in E theta, so that's going to just give you the partial of G with respect to R. Partial with respect to T on this product. Well, there's a T in this basis vector, so you get 2 terms. Here you get the partial with respect to T on F. ER does not get differentiated. And here it's F times the derivative of ER with respect to T. The derivative of ER, that's ET. So you get this undifferentiated term, F, that will show up in the answer. And then you got to do the same thing on this product. And you're differentiating with respect to T. This product has an ET in it, or E theta. Well, that derivative has to be accounted for. Well, here you get the partial of just G. And when you take the partial with on the basis vector, you get minus ER. And so you get this undifferentiated G with ER. Put all of that together. Grouping terms ER here and ET here. You have 3 terms here and 3 terms here. And you can just bring these things down from ER here, and you get a term from ER here, and you get an ER here. Notice an undifferentiated term here. Notice an undifferentiated term here. And if you want to put that in a matrix times a vector, then here you'll have FR, and from here you get a GR, and then these terms f sub t minus g over r, f plus g theta over r. That does not look like just take a gradient, because if you just took a gradient, you would not get this undifferentiated term here or here. So it is the differentiation of the basis vectors that changes your expectations of what this is going to turn out looking like in the general or symbolic case. Can we do what we just did with pencil and paper in Maple? So, student vector calculus package, a little bit of typesetting, but we need to set the background coordinates to polar, and in a moment I will show you why. We need a vector field in polar coordinates. Because I've set the background coordinates to polar, I don't have to tell the vector field command that we're in polar coordinates. It will inherit that coordinate system from the background. We have a vector field for the direction. It will be in polar. And then I want this symbol FR or F sub R and G sub R to stand for derivative, because otherwise subscripts don't normally stand for derivatives. Okay, I want to use this del operator here, v dot del. There's no way to tell the del what the coordinate system is unless you set the background coordinates to polar. So if you want to use this notation, v dot del, then you've got to change the background coordinate system. You apply that to f. Well, this is the first thing you get. You have derivatives, right? It's the partial with respect to r. It's partial with respect to theta. You have a complex sine of r. You see, the arctangent could be positive or negative, and r has to compensate as the angle goes from 360. That's why this is so messy looking. So you begin to simplify stuff. Assume r greater than 0 and t in the real range keeps everything positive, so it looks a little bit more compact. If you change the d operator to diff, then the typesetting command will set the partial derivative as a subscript. That's even easier to read. And if we collect, it's even easier then to read, because you can see here FR, there's your FR, here's your G sub R, and you've got F theta minus G, here's the minus sign, over R. It's this term, and this is F plus G sub T, F plus G sub T over R, and the A and the B will be over here as a column vector. So you can do this in Maple in the symbolic case. Here's one way to do it. Can we do this in Maple via first principles? Will we get the same thing? Can we do that? Okay, we want to work from first principles. Student vector calculus package. Some typesetting to make things simpler. First principles, we define the line that we're going to work march along in polar coordinates. We've done this before, r and theta. F evaluated r and theta, and a dummy representation of the basis vector er. G, the dummy representation of the vector e theta. Differentiate with respect to the parameter along that line, set it equal to 0. We're using generic x and y, but that's r cos theta, r sine theta. Do some simplifying. R greater than 0, restrict the range on theta so that you don't have the minus sign problem to deal with. Otherwise, this is 3 lines long. Okay, derivative. This is a partial with respect to r. This is a basis vector. This is the partial with respect to r on g. This is the derivative of the basis vector. So let's see if we can clean some of that up. Derivative of the basis vector er we know is et. Derivative of the basis vector et we know is minus er. That shrinks this a little bit. Convert this to diff notation. The denotation becomes partial. The typesetting command recognizes the partial, and it will write it as a subscript, so we shrink it a little bit more. Let's collect with respect to the basis vectors, because we have an et here, and we have an et here. So let's collect with respect to those basis vectors. And we have this component, and we have this component. Let's see if we can make that a little easier to read. This I'm going to call uppercase U, because it is the polar equivalent of the Cartesian vector with little u, little v. And the other component, I use a v. I'll just brute force make those changes so I can read this more easily. Here's the ER component, here's the E theta component. I want to pull those out in a way that these two r's cancel. So I use, take the coefficient, then I collect FR here, and two terms here for the V component. Same thing here, GR, and two components for the V component, two terms for the V component. If we write these terms in matrix vector notation, we're going to have FR here, so that FR there, and the GR down there, and then F theta minus G over R, and down here it's F plus G theta over R UV. That same matrix here, what are the big U and the big V? It's the polar equivalent of the Cartesian vector, whose components are U and V. Again, looking for a way to verify that all of this symbol pushing is correct, let's do this example. So we have this vector field in Cartesian coordinates, x squared, y cubed, x cubed minus y squared. Bring that to polar coordinates. Make the components functions so that you can easily make evaluations of those functions. The point has this as its angle. The radius is 5 with this angle, so that's the polar representation of the point. And let's implement this product. D1, that's the derivative with respect to R, evaluated at the point P, derivative with respect to R on G, and then these fractions here, right? This is F theta evaluated P, this is G evaluated P, R is 5. Similarly, down here, F plus G theta, F at P, G theta, that's the theta derivative evaluated P, U, cosine, theta, cosine of the arctangent. Lo and behold, it is exactly what it's supposed to be. It is what we got several times when we did this example before. But here's a question. That's why it's in yellow. This is something that didn't work. And it plagued me for a very long time because I thought it was something wrong. So we have a Cartesian vector field, Cartesian direction vector. Take the directional derivative. This is what it looks like in Cartesian coordinates. And I said, let's just map that to polar coordinates. And so this is a mapping to polar coordinates. Look what you get. Derivative, 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 derivative. There are no undifferentiated terms. Is this right or wrong? Well, it turns out that it's not a fault of Maple. It's not a fault of, because I dug into what Maple's commands are doing and so forth. It's just that mathematically this is incorrect, because if you take the derivative in polar coordinates, in Cartesian coordinates, you are not differentiating the basis vectors. And then you map to polar coordinates, you miss that opportunity to differentiate the basis vectors. This can't ever come out right, because it's mathematically just plain incorrect. But surprisingly, this works. Let's take a look at it. Initialize. Polar vector fields. Bring them back to Cartesian coordinates. Compute the directional derivative in Cartesian coordinates. Bring that back to polar coordinates, and you get the right stuff. Partial with respect to r, partial with respect to r. You get the undifferentiated term here and the undifferentiated term there. But why does it work? And the reason why it works is when you bring this polar field back to Cartesian coordinates, Maple brings back the polar field to this Cartesian field, and it is this term, x over r, it's a trig term. That's where the product takes place, and that's how you get the undifferentiated terms when you differentiate this product. So I don't think it's working because the basis vectors are being handled properly, but I think that this is just an accident that this works correctly. Well, will the directional diff command give us this same result? Let's try that. So student vector calculus package, a little bit of notational finesse. Vector field in polar coordinates. Vector field in polar coordinates. Directional diff applied to this polar field, polar direction vector. Tell Maple you work in polar coordinates. Some simplification, r greater than 0, theta in a range that deals with the minus sign. Things get shrunk down to this. We have derivative with the denotation. If you switch to diff, then the typesetting can kick in and write that derivative as a subscript, which I just find easier to read. And then let's grab each of these two components, do a collect, so that this r canceled with this r in this piece, but not in that piece because there's nothing to cancel it with. And you have this is the polar first coordinate of the direction vector, and this will be the second component. And if we write that stuff here in a way that's recognizable, you have derivative with respect to r. You do the same thing here. You get derivative with respect to r. This is the top component, the upper component here. Then you have the derivative with respect to theta, g. You need a minus sign here to make this thing the correct second component. And do the same thing here. And we recognize that this is the same thing that we got when we did it from first principles. So far we've been working with unit basis vectors because that's what Maple uses in its vector calculus package. But the calculation is really supposed to be done in differential geometry using covariant derivative. But as soon as you go into differential geometry, you work with the natural basis vectors, which are not normalized. there are no scale factors. Let's take a look at what happens if we work in the natural basis vectors. Basis vectors. Okay, you differentiate the position vector with respect to the two variables, the parameters r and theta. This vector is the same, it will be unit, but e theta picks up a factor of r, and it is not normalized away. The derivatives change now, right? The derivative of er with respect to r is going to still be 0. Derivative of er with respect to theta, you're going to get minus sine cosine. It's this piece right here. Well, this piece right here is the natural e theta divided by r. Right? You divide that r. Then you take the r derivative of this vector. You knock off this r, so it's e theta over r. And then you take the t derivative, and this becomes minus cosine. This becomes minus sine, so it's minus r er. The gradient operator in the natural basis vectors, there are no scale factors, so it's er partial with respect to r and e theta partial with respect to theta. Now let's take a look at the direction vector. Well, let's use a and b as the components with respect to er and e theta. Natural. Now, if you check how u v in Cartesian coordinates maps over to polar coordinates using the natural basis vectors, there is a factor in the second component divided by r. So this b is this second component, but it's divided by r. So now take direction vector dot operator, gradient operator, er dot er survives, e theta dot e theta survives, so you get a partial r and b partial theta. Apply that to a vector. A partial r, b partial theta. Vector, we'll call it f er plus g e theta. Partial with respect to r is going to apply to this product and this product. So here's the partial r with respect to the first product and then with respect to the second product. And b e theta, b d theta is going to apply to this product and this product. So there is being applied to the first product, there is being applied to the second product. Let's see what you get. This one, partial with respect to r, was only going to affect this f because there's no r in er. So you just get f sub r. This one, you're going to get two terms because you're going to differentiate g, that's this piece, partial on g, but then you have to take the r derivative of e theta. The r derivative of e theta is e theta over r, so here is where the undifferentiated g shows up. Then you take the t derivative of this product. Well, there's a t in er, so you're going to get two terms. You're going to get partial with respect to theta on the f, and then you're going to get the undifferentiated f and the partial on er, that's et over r. So you get the undifferentiated f term there. Then you take the t derivative of this product. There's a t in g and there's a t in et. So you get g differentiated with respect to t, and then you differentiate et, you get minus r er, so you get an undifferentiated g. there are now 7 terms, not 6. When you collect all the ER terms and the E theta terms, there were 3 here, but now there are 4 here. And if you dispense them into a matrix vector representation, there's your FR, there's your F theta, and there's your RG. This fellow goes down, let's take the G sub R first, and then G over R here, and then the 2 terms that are multiplying B, F over R, and dg d theta. Now I've used A and B for simplicity, but A and B, if you're starting out with a U and V in Cartesian coordinates, okay, they become component. The component we have been seeing, you can see right up there, but its second component is divided by R. Again, we would like to verify what we just worked out with a pencil and paper. Can we get this result using first principles? So some initializations here. These are notational devices, and we're going to work from first principles. So here is our R and our theta that in polar coordinates takes us along a line, and we have these calculations to examine. F and G are the components of our vector evaluated along that line in polar coordinates, so it's RT. The basis vector, the big R, is just a function of t. To get the R into this picture, I found it simpler to put the factor of R in front of the E theta and keep E theta as a function of just t. It turned out to be simpler to do that. So then you take the derivative with respect to S, and we're dealing with x and y as the base point, so x is our cos, y is our sine. Do the standard simplifications here, otherwise this is three lines long. We have derivatives on big E, and we have big E, and same for big R. So let's replace the derivative with respect to t with et, and derivative of et with respect to t as minus er. So that's a little bit shorter. Convert this to diff notation so that the typesetting commands allow derivatives on f and g to be represented in terms of subscripts. So you can see now you have subscripts that represent derivatives. Collect with respect to big R and big E. So you get these two bunches. And this I will call big U for the minute. And then the other component, big V. We have an ET floating around right there. Let's now convert that to little e, the natural basis vector, over R, because ET is big E, little e over R. So we compress this further to this form. I would like these two R's here to cancel, so I use a collect, and you get this partial with respect to R in these two terms. This is U and that's V. And over here, there are 4 terms. Here are 3. So again, you get those 7 terms. You want a cancellation to take place here, right? R squared and an R. So U, this will be G over R, and this will be just dg dr, and here you get dg dt theta, and then you get the cancellation of this R squared, because there's an R over here. See this R here? this r here. Well, that's why this g theta derivative has no r under it. But f is multiplied by this r and is divided by r squared. That's why it ends up over r. So if we just write what we're looking at, we have 7 terms, right? 1, 2, 3, 4, 5, 6, 7. These are what we obtained when we worked with pencil and paper symbolically. And this big U and this big V, there's the U, and this is the V. You can see we correctly brought that V into polar coordinates in terms of the natural basis vectors. And if you just want to take a comparison to what we got using unit basis vectors, it's different. Okay, and it is the basis vectors that make the difference. It's nice to compare the results you get with unit basis vectors and natural basis vectors. So here's an attempt at reconciliation. Position vector, r cos, r sine. Little e, that's a natural basis vector. It's the same as the unit vector. So the caret, standard notation for unit vector. E theta is natural, differentiate with respect to theta. Pick up an r here and an r here. So it's r times the unit vector. Okay, a vector referred to natural coordinates. You want to refer that to unit coordinates. So there's the extra r right here. That's this extra r right here. Now, if you move that r over to the component, then what's left is the unit vector. So this is f, and this product is g. And when you have a direction vector, uv, referred to natural basis vectors, u stays u. But there's an r factor here, which you bring over and put with the v in order that this be a unit vector. And so the v is big V times r. So to summarize here, what happens when you take derivatives? You take the derivative of f with respect to r, you are differentiating a with respect to r. F with respect to theta, differentiating a with respect to theta. When you differentiate g with respect to r, you are differentiating this product. So you get 2 terms. R times the r derivative of b, and then you just get a b factor because you differentiated the r. And when you differentiate g with respect to theta, you differentiate just b because there's no theta in r. So take the expression that you got when you used unit basis vectors. It looked like this. The f dr is the a dr, and u is u. The f d theta is the a d theta, but g is br, and the little v is vr. And now you're talking natural basis vector. dg dr, 2 terms. R, br plus b. U stays, little u and bu are the same. And then this guy, you have dg d theta, that's r b theta. You have this f is a. the little v, big V times r. The unit basis vector here is natural basis vector divided by r. Do a little cleanup. Okay, you have an r here, you have an r here. They cancel, you get just these two terms. You have an r out here. That's going to knock off this r here, but it's going to put an r under this b. These two terms cancel. So you get b theta a over r, but this r has knocked off that r. And so this is what you get when you have the natural basis vectors, and there are 7 terms, 3 here and 4 here. And now a word about the covariant derivative, because this is the ultimate test for whether or not we've got things right. So this is a pencil and paper, a sketch of doing the directional derivative from first principles using basis vectors that are themselves functions of position. This is really what the vector looks like using the Einstein summation convention. This is really a sum. So this is the component evaluated along the path, and this is the basis vector evaluated along the path. When you take the derivative set it equal to 0, you are taking the derivative of a product. So this is the derivative. These two things make up the derivative of the component times the basis vector. And here you are differentiating the basis vector. And the secret of all of this differential geometry stuff is that the derivative of the basis vector can be expressed as a linear combination of the basis vectors. And the coefficients in those linear combinations are the Christoffel symbols. That's all that's ever happening here in the definition of the covariant derivative. Okay, so that's the background to covariant derivative that will give you an inkling as to what will happen next. So now we're going to take the directional derivative via this covariant derivative machinery. Okay, so I'm going to do it here in the physics package. I'm going to let the physics package get me the covariant derivative. So you set up the metric in Euclidean space and you transform it over to polar coordinates, right? Because here are the transformation equations for polar coordinates. You define the vector that you're going to differentiate. This is the direction vector, and here's some notational stuff. And this is the notation for getting the covariant derivative. And I'm using this machinery to display it. You'll notice it has 7 terms. These are the terms that we've seen before. And if we run up here and take a quick look, and maybe we'll go up here, it's these terms here, okay? We've gotten the covariant derivative. The covariant derivative is summed with the direction vector. The Einstein summation convention takes place here. The lower index down here with the upper index up here. Now if you look at how Maple displays this, the summation is on this lower index. It's a column, so you're summing on the column index, so you've got to write W as a row vector in the front on the left side. So it's row times the matrix. This, if you study it carefully, is exactly what we got before. All right, if R with alpha, beta is F theta minus RG, and so forth. So this covariant derivative gives us exactly what we have been computing by hand and various other subterfuges. So we're getting the right stuff. We haven't made any mistakes. And again, let's use an example to make sure that everything that we're doing is on the up and up. So this example is familiar. We have the vector field in Cartesian coordinates is x squared y cubed, x cubed minus y squared. Map that to polar coordinates. Make functions of the polar coordinate components. And here's the point where you want to evaluate, because we know what the answer is supposed to be for this directional derivative. So to implement this computation, d1 is partial with respect to r on this first component, evaluated at the point P, etc. Let's see, g over r, so here's g over r is 5 because we picked 3 whole 5. The vector here, direction vector, has an r in the bottom, so you divide by 5. Carry out this computation. It is exactly what we have been getting before. So this is the correct representation of the covariant derivative in polar coordinates if you use natural basis vectors. It's correct. There is one other place in Maple where this directional derivative can be computed, and that's in the differential geometry package, which has a command for the directional covariant derivative. Now, there's a lot of machinery here that you have to set up in order to make use of this package. I got it all in place here in case anybody wants to run through it. Polar coordinates, so here are the Christoffel symbols for polar coordinates and how you get to see some stuff. This is how you define the vector field you want to differentiate. This is the direction vector. And here is the command, directional covariant derivative. This is what it ends up looking like. It's a very strange notation. Here is a way to make it show up as an array. This is the array. If you take just the covariant derivative, you see it's this thing with the 7 terms that we have been getting. So again, here is Maple confirming that if you're working in natural basis vectors, so you use differential geometry tools, either in the physics package or in the differential geometry package, you do get the right stuff. And finally, a summary of what we have seen and how we got those results. So if you're working with a scalar, Cartesian coordinates, scalar in polar coordinates, these are the things that we could use in Maple. If you are looking at directional derivative of a vector, this is in Cartesian coordinates. This is what you get if you are using unit basis vectors, and this is how we obtained it in Maple. And if you're looking at a vector using natural basis vectors, this is the result. And we did it with first principles, and we did it with the covariant derivative in 2 different ways. And if you want a copy of this worksheet, you can email me. Here's my email address, and I'll send you this worksheet, because there's certainly a lot of material in here that needs to be absorbed slowly and carefully.